Our second speaker of the second technical session is Bassam Alrifaee, and he is currently at the University of Delaware. However, he is more long-term at RWTH Aachen University in Germany. So we're very happy that he was able to make it to the Maryland Robotics Center Research Symposium.
Yeah, thank you so much, Michael. Thank you for giving me the opportunity to talk here. And I would like to start the talk just with a short introduction about my home university, as I am the only one from outside the US. Yeah, RWTH is founded 150 years ago, and it is the largest technical university in Germany. We have a lot of students, brilliant students. One of them is sitting here, Johannes. And yeah, we have also international students and so on. And we have the highest number of alumni sitting as CEOs in DAX companies. So DAX you can compare with S&P 500 in the US, so the biggest German companies. And myself, my background is, I started in computer science, automation, engineering, moved on to mechanical engineering, where I studied network control systems, and moved back to computer science, where I'm doing cyber physical systems. And this is the focus of my group. So we study the combination of control, optimization, and communication. And this makes something we call network predictive control. We combine this with software architectures. You saw some of them today at the poster of Johannes. And also with localization systems, we look at infrastructure-based localization. I would like to start the talk looking at this nice video. This is a very complex scenario. We have a lot of robots driving about this area. Here in the middle, we have an intersection where the vehicles have to coordinate to not collide with each other and to drive safely and efficiently as fast as possible. We have here in the ring the highway area with highway entrances and exits. And if you are interested how we implement such a complex scenario, you have to listen to this talk. So I would like to start the talk with this thought experiment. So especially in the post-COVID time, you have experienced it by yourself or you observed it. Two pedestrians are walking towards each other. They try to avoid each other once, twice, and maybe they resolve the situation with a smile, or they pass by each other somehow. Yeah, and imagine we extend this to N pedestrians. Have you been to Japan, Tokyo, Shibuya crossing? It was amazing to observe this the first time in my life, and I have it always in my presentations. And now I would like to involve you in this presentation. So this is a simple mathematical problem. So choose a number between 0 and 100, and the winner of you will be the closest to half of the average. I give you only 3 seconds to think about a number, grab a number, put in your head, I'll come back to you in 3 seconds. Okay, who said 12.5? Who is next to 12.5? Maybe 10? Yes, perfect. Tell us how you came to this.
I already took a class on game theory, so like in that class we already did something similar and we got that the average was close to that.
Yes. So it is from game theory, so if you have class in game theory, it's very easy. So some people would say we are looking at number between 0 and 100, and we are looking at the average, so some people would say 50. So, but the majority will go further and say, okay, we are looking at the half of the average, so the majority will say 25, but the half of the majority is then 12.5. So if you would say 12.5, you would win. And I conducted this experiment several times, and it depends on the class size. It's close to 12.5. And why I'm showing you this at the beginning of the presentation, to get your thinking now into network thinking. So the decision of quality of individuals is affected by the decisions of the others. And in my group, we study the coordination problem in 3 levels. We look at the method, and in the method, we look how we can reduce the computation time of the agents to get solutions in real time. We look at the interaction in a mixed system between humans and robots, and also we look at enhancing the quality of control. In the application layer, I'm going to show you some applications during this presentation, and we get our methods through application to real-time experiments. So one method to solve the problems is using centralized predictive control. We formulate a centralized problem where we gather all information in the system, solve a huge problem, and communicate the solutions back to the agents. This is not applicable in practice. It has a high computation time and single point of failure, but we implement it as a benchmark to compare it with our distributed strategies. The first distributed strategy I'm showing is the cooperative one. We decompose the centralized problem into small centralized problems. So each agent optimizes for itself and its neighbors. And this is not going to work because of this property, which is called the prediction consistency property. Some people call it the planning mismatch or the information asymmetry, and there are further names of this. And this property says the prediction consistency means that the plans used or computed in the optimization problem of an agent I at a time instant t for an agent j coincide with the plans computed by agent j itself at the same time instant. It was too long to read now. I need to breathe. So it means what I think now is what you think at this time. So what I think about you at this time, you think about yourself at this time. That's all. And this is very important to satisfy this property. Without the satisfaction of this property, we cannot talk about feasibility and stability of the network system. And this is an example or illustration why it doesn't work in cooperative control. So we have here an agent VA and its perspective. So it sees B, C, and D, and B sees additionally E and F. So A doesn't have the information about E and F, and this leads to the mismatch. So in the literature, there are some solutions using sequential and iterative approaches, and our approach we presented is the synchronization-based cooperative distributed MPC. You can read more about it in the paper, but I am going to present the next one is the non-cooperative distributed MPC. And here, the agents communicate their optimized inputs to each other to compute or to take each other into consideration. And this is also not going to work. There's some mismatch, and we have also to come up with some solutions. And in general, the solutions are also somehow sequential and iterative. And the one we presented is the priority-based non-cooperative distributed MPC. We get some structure into the system to be able to get feasible solutions, to reduce the computation time, and to design the order of computations in the system. And now I would like you to play this game. So it's chess game and checkmate in 2 moves. So you are playing with the white figures. So raise your hand if you got the solution. Yes, please. Yes, sounds good. Yes, you started very well. So then the queen down to C2. So this is the solution. So why I am showing this, just for me to have a small break to drink some water and for you to get again into the network thinking. So we have here also some predictive control, and you have also to have a model of the game, and you have also to interact with the other player. So you have to think what the other player is thinking, and you have to think what the other player is thinking about you, and so on. And now I would like to show some applications of this. So here on the left-hand side, we see an intersection. The vehicle should drive as efficient as possible, and of course, safely. And this we implemented using our priority-based strategy. And here is very well-known example from robotics. So vehicles are distributed around the area, and they are assigned target positions and orientations, which we call poses. I think you showed one of these examples, Spring. And we used this method also to guide them as fast as possible to their targets and also efficient. So till now, it was methods and some simulations, but not exciting enough. We need some experiments. And actually, this is a very exciting example of racing, because in racing, the vehicles, they compete, but at the same time, they have to take each other into consideration to drive also safely. So we have here, so the coordination problem is competing and coordination for safety. So this is why this is more exciting than the other applications. And till now was simulation, and this is a video taken from my PhD, where I ran some experiments with this model vehicle. I was avoiding an expensive car to show I trust my algorithms, but this was a lot of logistic works, going outside, transporting the robots, and also marking the area where they are allowed to drive, transporting all the parts outside, and it was very painful, working through the nights, sometimes to get the truck here. And I wanted my PhD students not to have this pain. That's why I started the Cyber Physical Mobility Lab. So it's somehow between simulation and real world. And here are the features of the Cyber Physical Mobility Lab. So it's open source. So I opened everything. You can go to our website, find the software, documentation, everything. You can rebuild the lab in your lab. And it is remotely accessible. If you don't have the resources to rebuild it, you can just go to our website and check out our remote access. So you can remotely access it and use it. We support centralized and distributed computations. This is very important and unique for our test bed. We support deterministic computation model, and this means our experiments are reproducible. And we have also a digital twin of the lab, which allows the seamless extension of our MiCAs. Maybe you saw at the poster. So I have 20 of this guy in the lab. So just come and see it after the presentation. I'll be happy to explain it to you and to show you how to rebuild this. And there are also, of course, some related works. Now I am visiting Scholar at the University of Delaware. They have also their scaled city. This is actually our CPM lab. At the University of the state university, no, how it is called, the ASU. Yes, so Arizona State University, yes. So Spring has the Go chart, and it develops to Chatterpolis. Also, there is one at Cambridge, the Proro Club. The Ducky Town is very well known from MIT, and also the Repertorium at Georgia Tech. This is the structure of, or the architecture, the functional architecture of my testbed. So it is modular. I built it according to Sense Plan Act, and I have also some infrastructure parts in the software. And the focus of my testbed is on coordination and decision making. And here we get there. So if you use the methods I've shown, the applications, and you have such a testbed, or you access it remotely, you can implement such a complex scenario with in the testbed up to 20 model scale vehicles. And here how it feels to be in one of the new cars. So we are studying also the human-machine interaction, and we recorded this video for one of our proposals with our collaborators. And actually, I cannot look for a long time at this video because I get dizzy. So when you look at the bird view of the CPM lab, you feel the vehicles are driving fast, but not fast enough. But if you look at one of them, so from the first person view, yes, and we wanted to show we can also study collisions in there and how humans would react to them. And this is a video taken from our remote access. So here is our real testbed. And here is the digital twin. And here you can show some of the signals. And here is the programming interface. You don't need to install anything. You can just go to the browser, register. The registration is very easy. And you can start with a default project. And yeah, you can test out the Physical Mobility Lab. And this is exciting, but it's more exciting to get alive. Okay, maybe I can do this. So we are now going to try to access the Physical Mobility Lab in real. So for this, I have to go to remote access on the website. So maybe I can see if the student is there. So you didn't want to hide. Anyway, I go to login. So the registration is very easy. You just need to put your email address and password, and you are there. And here I am logged in now. And you can start with one of the default scenarios. I'm going now to start the central routing. I'm going to request a session. And I hope it will work. So somebody is in the chat. Yes, I am here. Very good. So now, let's hope I can connect. So you have two ways. So the one way you download the simulation, you develop your algorithms, then you can submit your software. We will run it when we have time and submit the results back to you. The other way, if you wouldn't have live remote access, you can, of course, submit a request, and my students will see that. They will arrange an appointment with you, and you will have remote access. So here we see the webcam of the, maybe we can turn off this slide to see it. Okay, don't worry, maybe people are imagining what is happening. Yes. Yes, now we are in the cinema. Yes, so here is the real test bed, and here is the digital twin, and everything is now ready to start, and I'm going to start the CPM lab from here. So please work. So it's working. So I started my software for coordination and planning of the vehicles here from Maryland, and the lab is now running in Aachen, Germany. And I can look at some of the measures here. I can add also some more. I can choose the vehicle I would like to look at the signals. And what we are looking now at is the battery level. So it's not very interesting, but it's one of them. So I can also stop the simulation, the access from here. So the vehicle stopped there. And please give a big applause to my student there. It's now 9 p.m. in the night, and he just went there for this. Thank you so much, Lucas. So here's Lucas saying hello to you. Now we continue our presentation. So Lucas, you can go and enjoy yourself. So maybe I can stay for a minute on the website. So actually, I can hide this. So this is the website of the Cyber Physical Mobility Lab. You can go here and see the whole documentation of the lab. We have documented everything. So you can just rebuild it, or you can go, of course, to the remote access I have shown. You can go to GitHub and see the whole software. You can use it. You can see also applications there. You can go to resources, and you will find the publications related to the test bed. And you can go to education and find 3 courses which we provide online. So if you want to learn programming, C++, or if you would like to learn control or connected automated vehicles, you can check out the courses. Additionally, we have also a competition called CPM Olympics. So the first edition was last year, and this year we are running a second one. It will start soon, so you can jump in and learn about it. So maybe I can also show you. So you can go to remote access, and in remote access we have the Academy to learn programming, and we have Olympics. So you can go there and learn about the competition. You can win up to 2,000 euros this year, and here you can get some of the information on the competition. So here are some data about our outreach and the connection also to the smart city in Delaware. So maybe you have checked out the poster. So this is one of our work. And if you haven't checked out the poster, here is the video. So here the vehicles are driving in reality in the scaled city in Delaware. And this is our planner from CPM. And the 2 test beds are now connected. So if you write software for the one of the test beds, you can seamlessly go and apply this in the other test bed. So this is a very nice feature, and we would like to extend this to more test beds. So if you have here at Maryland something similar, we would like to extend it. So I talked also to Spring. We are going also maybe to extend it to the Chattapolis. Maybe I don't need a summary, so I showed some methods, some applications, and some experiments. And I would like to thank my group for the great work and also for the whole remote access support and, of course, for the whole interface programming and so on. And I would like to discuss with you now.
A couple of questions. Very impressive international live demo. First time that I've seen that in my own life, so very cool.
So for the physical test beds, are the vehicles available at all times, or do we need to wait for someone to place them in the test beds themselves for them to be available?
You need to book an appointment with us because sometimes it is in the night for us, so it's in the day for you. We have time difference. And actually, in Germany, the rules are somehow strict. We are not allowed to run the test bed if nobody is in the room. So we were thinking about what you described, because we have the go-to formation, so we can just run one experiment after the other. This is possible, but somebody should be available in the test bed. So you need to book an appointment.
Yeah, because I imagine it can be done autonomously, where after an experiment you can run an algorithm that resets the vehicles to some starting position.
Yes. So this is possible now. We have this algorithm called go-to formation. So the vehicles start in arbitrary positions. They go to their starting poses, and they start the experiment. And after that, they go to the next experiment, and so on. But not 24 hours.
Okay, thank you.
Right.
Other questions for the speaker? Oh.
I just wanted to ask about the battery life on these, because is this hardware that you made yourself or your lab?
The battery?
Yeah, right, the battery.
Yes, it's out-of-the-shelf battery, so it is lithium air battery. It's good. It runs for maybe 2-3 hours. You can check out. So it can run more than I can focus on my research. So I cannot focus more than maybe 1.5 hours. Then I need a break or a coffee break. And this can run maybe 2-3 hours.
Okay, I think let's thank our speaker one more time.
Thank you.